Just one quick reminder before we get started. The last reminder that today, immediately following this session, there will be a special reception up on the second floor. There'll be food, drinks, possibly cake. And at 5:30, we're going to be starting our award-winning first run of the Tony Awards. So make sure to come there and sharpen your good Tony stories because, well, she should be leaving blushing.
2 days of blushing. Oh, you're gonna blush. Wait. All of you wait. You'll see. You'll all see.
And people can take photos, videos, and send them to me. They'll really need them 10 years from now for me showing.
Okay, welcome back to the last session of the day, which is another student session, and I'm happy to present Robert.
Thanks. All right. Yeah, so I'm gonna differentiate a little bit from the other talks. I'm not gonna talk about anything technical. I'm not even really gonna use the board except maybe to draw one picture. I just want to tell some stories, more or less, which I think, I don't know. So the goal is to embarrass Tony a little bit. So this is what I want to do. So, okay. So a little bit about me, I'm one of Tony's many grad students. I joined Toronto in January 2013, halfway through the year. Getting into Toronto was funny for me because I only applied to Toronto on the story is really weird. Do you know the story actually?
I just give Antonina all the credit.
Yeah. Yeah, so Antonina invited Steve to Newfoundland to give a talk. And then I met him, of course, when he talked. And then I ended up like just chatting with him at a party at your house. And then,
Chatting as in, here is my idea of how you could solve a tree relation problem. There is this approach and this approach. I already thought about that one and that didn't work, but that one might.
Yeah, it's true. You're making me blush. And yeah, and then we talked for a while, and then eventually Steve was like, "Oh, so are you applying to grad school?" And I was like, "Yeah, probably. I don't know. I hadn't really thought about it." And he was like, "You should probably apply to Toronto." So I was like, "Oh, okay." So I applied to Toronto, and I only applied that year because I wasn't planning on graduating at that time. And then so I only applied to Toronto, and then I got in, and then I was like, "Oh, okay. Well, now I have to graduate like right now." So that's why I ended up coming in January as opposed to September. So I had to like cram the rest of my program into one thing. But anyways, yeah, even though getting into Toronto was a funny thing, kind of a funny path, it was like the perfect fit for me. There was really like, I really felt like no pressure to perform in some sense, like other than the pressure that I was kind of putting on myself, of which I think I was putting a lot of pressure on myself, like many grad students do. But there was never any pressure to perform, particularly from either Tony nor Steve. Like all they ever really wanted to do was like talk about science, and I always felt really free to like work on whatever problems I wanted to, which was like a really good fit. And there's a couple of funny things. I mean, there's a lot of funny stories that I could tell. One funny story that I'll tell is, or do you remember the time? I don't know if I told you this story actually. So you asked me once to substitute in for your second year, like algorithms and data structures class. Did I tell you this story?
No, but I have a feeling that I can imagine what the outcome was.
What was the, what do you think it was?
Probably my review said, "Too bad that Robert didn't teach the whole
No, no, that was definitely not what happened. I showed up to class. It was like about maybe a month into this. It was maybe a month into this semester. So Tony was of course going away to a conference or something, and I was around. So I was like, yeah, I can cover this class, teaching DFS or something. So I walked into the class, and I walked in really flustered. Like I walked in like, oh my God, it's unbelievable. I walked in and I came in the board, and I went up to the board and I was like, okay, hello everybody. My name is Tony Patassi. And I didn't actually know I was supposed to be teaching the course this semester. And so some lady has just been coming in every day and teaching this course the whole time. And I actually had them going. Like I did this, and then no one laughed. And they all slowly, I remember focusing on one student, and I was just watching her mouth just go. And then after like 5 minutes of keeping this up, I was like, okay, I'm kidding, right? Like, I'm kidding. My name's Robert. I'm Tony's grad student. And everybody was like, oh, like it was like the whole room breathed out. So yeah, probably why I didn't tell you that story. So, yeah, it's funny because like I guess none of them ever mentioned that to you. But anyways, yeah. So this is an idea of how relaxed the atmosphere at Toronto was, or at least how relaxed I tried to make it. But anyways, like one thing I really want to talk about is like talking about collaborating with Tony as a grad student. Like I said, I kind of like to work on everything. Like I really don't really constrain myself when I like to work on. I like to work on lower bounds. I love complexity theory, but I mean, I really don't constrain myself to one sort of thing. I like to think about lots of things. And Tony's the exact same way. Like she likes to think about almost everything, right? And she's made all these fantastic contributions in all these different areas. So, you know, for that reason, I think like it's a really good fit. Whenever we would work together, you know, I feel like we would hop after we very quickly we would like work on a problem and then get stuck and then be like, oh, maybe we should think about something else, and then think about something else for a couple of months. And it was like, I don't know, it was very fluid, and I really liked that kind of working, and I like that kind of like it always felt like we were kind of on the same wavelength in that sense. So I really appreciate that, and that really gave me the model for like how to collaborate, I think, with other people and also my own students who like now who I don't know, I think have a very casual relationship. We like to talk about lots of things, right, Stefano? I don't know, what do you think?
Sure.
Okay, anyways, so one of the things about Tony, one of the things about working with Tony that I'm sure that everybody knows is that like, this is something that I really learned from her, I think, is how everything is completely intuitive for her, like just complete intuition. And she'll describe the most, like, if you could open up some scary yellow book and, you know, pick a theorem in it, and you'll have no idea what's going on in it. And then you can go ask her and she'll just be like, oh yeah. And then she'll just give you this like super stripped down concrete example that just completely explains everything. And like, it like, sometimes I feel like, I don't know, like she's so good at math, but like, she doesn't know the name of anything. So and I'll be like, oh, it's like this. And I'll say like a math thing, like, oh yeah, that's like an ultra filter. And she'll be like, yeah. And she'll be like, I don't know what you're talking about. I have a very vivid memory of a meeting that we had where I was explaining some ultra product construction because I thought it was related to something. And then we walked out of the meeting, we ran into someone in the hall, maybe it was Steve. And you said, the first thing that you said was like, oh my God, I think Robert almost killed me. But anyways, but then, yeah, and like, it wasn't super complicated math. It's like she understood exactly everything that was going on. It was just that she understood it in her own language, right? And that was something that I really took away. It's like I really probably one of the biggest lessons I learned during grad school was like, you really have to learn everything in your own language, and you cannot, now I cannot listen to other people explain things. Like I have to go away and like figure it out myself. And I feel like that was like a big lesson that I really learned from Tony. Another thing is that like with Tony is that it was so casual that like, I feel like, I hope that other people have this kind of relationship with their advisor, but I feel like we have a lot of inside jokes. And so I'm going to draw a picture and I'm going to see if you, oh no, let's see if you remember it. Do you remember this? That is the tattoo. No, that's what it was. Well, there was multiple, I guess. Somebody else did this. But yeah. So we have this. Yeah, right. So yeah, and this is exactly my point. Like this is the level of relationship that like we had, right? When we were, do you remember this, Dennis? You should remember this picture too.
Oh, it's familiar.
Yeah. We were working on this paper that actually led to both the stabbing planes paper and the random CNFs paper with Dennis, me, Tony, and Noah. And we kept making the same mistake in some upper bound argument over and over and over and over again for like 6 months, I think. It kept looking different every single time. And then eventually we were just like, oh my God, we're just gonna have to tattoo this on our body. Like, it's the only way that we're gonna remember it. And then eventually we just started calling that problem the tattoo. And then so like, I went and back and checked through my emails, and I have a whole bunch of emails just like titled tattoo. And like, it's like, no, this is the tattoo, this is the tattoo. And then I was thinking, ironically, I did just get a tattoo, but I didn't get the tattoo. So it's, yeah, anyways, so I don't know.
You still got space.
I still have space. That's true. I've got lots of body left. Okay, let's see. So those are the positive things about collaborating with Tony. So, the negative thing. Okay, not negative things. There's very little negative things about collaborating with Tony. I don't think. But like there are. I'm sure we all know that Tony has certain habits. Like she's not terribly good with computers. And in particular, another thing that's really funny is that like she has this weird thing that happens that like whenever you're in a meeting with her, usually several times a meeting, like what'll happen is, oh, sorry, 1 second. No, sorry. Yeah, sorry. Yeah, no, I'm giving a talk right now. Yeah, can I call you back? Yeah, okay. Yeah, so what's really annoying is that like several times a meeting, her phone will ring and she'll have a conversation that's exactly 4 sentences. I'm in a meeting. Can I call you? Who is calling you all the time? Like, I don't, who is it? It's them? It's, you know how many hours I, no. The other thing, when it comes, the other thing, Noah will have a lot more stories about Tony, but Tony's computers, I think. But like another thing was like, I think for like a full 2-year period, in order to compile a LaTeX file, you would email it to me so that I could compile it and then email it back. You don't remember this? Because LaTeX was broken on your computer for like 2 years.
I remember this.
I might just give it to my son-in-law.
The other thing that she would do all the time is like she would be like, I think she would you of course you have these big long email discussions where you're discussing theorems and proving things and all this fun stuff. And then eventually like a week will pass and you'll get busy or something and you'll forget to talk. And then you'll get an email from her in the same email chain being like, oh, I think we talked about this, but I can't find the email. Can you like send it to me? And it would be in the same email chain. Like I would just scroll up like 4 emails and like have to copy it and send it to her. Which actually I think I've done to you. So, oh yeah. So this is a bad habit that I'm picking up. Okay. All right, so 5 minutes left. Wow, I can't believe I actually managed to fill this. Okay, so I guess I want to talk now about maybe like a little bit more serious, well, not serious, but yeah. So when I finished my PhD, I think probably like many people, I felt like I had kind of lost direction a little bit. Like I kind of finished my thesis and I like submitted it and I had these postdocs lined up, which were good postdocs, right? Like I came to Simons and then I had the joint postdoc at IAS and Rutgers. So I was like really happy in that sense. I was excited to do it. But at the same time, like I also felt like I had kind of lost direction. Like I just kind of lost motivation to work for a bit. And I think this is probably pretty common, but it actually affected me. We never really talked about this explicitly, I don't think, although maybe you sensed something. But like, I never really talked about this with you or really with many people other than really close friends. And I actually almost left. I was seriously considering leaving academia to the point where I actually almost basically had a job lined up. A friend of mine had a startup. It was like he was doing really cool stuff, not programming, but like some solar panel sustainability thing. And he was like, basically invited me to be like person number 3. And I was like, oh, wow, okay, that sounds really cool actually. And I was feeling kind of weird about it. And so I seriously did consider it. And so then so I was kind of balancing these things in my head. And I think what happened to me is that like, maybe this happened to a lot of people too, is that I went to grad school kind of like, A, because I love the science, but also B, because I kind of wanted to prove to myself that I could do it. You know what I mean? And then when I proved to myself that I could do it, like some of that motivation just kind of left, I think, right? And then it was like, okay, well now all the motivation had to come from somewhere else. And it took me a couple of years to kind of reconfigure my motivations for that to make sense, right? So I don't know if you sense something or not, but there's this very vivid, for me, it's a very important thing that happened, which was when we were at Lower Bounds here in 2018, we went to Stanford that one day. Yeah. And that day was like super important to me. And yeah, like, wow, I didn't want to cry and I'm going to cry. Oh my God, I'm so sorry. Yeah, that day was actually like super important to me. Like, if it wasn't for that, I don't think I would have continued. Yeah, so to this day, I mean, like, we're still collaborating. And like, I still have like a weekly meeting in my calendar every week to meet with Tony, even though we skip most of them because one of us are busy. But it's still there. We still meet every week on Zoom. And I wouldn't have it any other way personally. So I just want to thank you for all the support. I want to thank you for being my favorite collaborator. Oh my God. Whew. Whew. Most of all, I want to thank you for teaching me how to be a scientist. All right, I love you, Tony.
Can I ask a question, Robert?
Yeah, sure.
How many academic grandkids does Tony have, thanks to you?
Oh, good question. Well, I mean, they're not official yet. Well, I haven't graduated yet. Yeah, I have 3 students right now. Yeah, and just hired a 4th. They all look alike.
Thank you.
Thanks, Robert. Are there any other questions?
I have a comment though. It reminds me, you're getting for blungent there. You know, in Saturday Night Live, Mike Myers used to say, you know, for blungent, talk amongst yourselves, you know, while he recomposes. And that reminds me that Tony was Rosanna Dana in one of our skits, and you know, Rosanna Dana was never better than you were. So for those who remember that, it was a star performance. Unfortunately, we didn't video things then. Let's do it again.
Any other questions? Speaking of technological difficulties, I had a grad student contemporary, Alan Skelly, who alleged that in order to search Google, Tony would go to Yahoo and type in Google.
I think somebody started a rumor that I Google. I had to Google. Anyways, it's nice and circular, but I don't think I did.
You could do it all through terminal, right?
No, I still use the eye.
Oh, yeah.
I don't know.
Tony, I remember during undergrad, you were telling me that sometimes you're purposely not learning new technology because you need space in your brain for, you know, more important things. And that was quite a novel idea to an undergrad me at the time. And I keep thinking about it all the time since then.
Hey, can you hear me?
Oh, Josh.
Yeah, I just wanted to, so Robert, I think your story about the Tony emailing you stuff to LaTeX, it actually happened around the time when I was a postdoc there. And I think Tony and I think actually Tony might have been sparing you because at the time I was using Dropbox for our IPS paper. And I think that was like the first time Tony had ever used Dropbox.
Yep.
And at one point, she like didn't understand that Dropbox was like synced across everyone's good, and so she actually deleted our Fox paper, and luckily I had a backup, but I think maybe that experience might have scared her, and she said, "No, I'm just going to email Robert the things and have him compile it, and I'm not going to mess with it." Yeah.
No, I do it that thing about getting rid of everything.
Any other comments? False rumors or anything? Okay, thanks again, Robert. Our next talk, I think, is by Sayak Chakrabarti. I'm not sure whether it's an online. Oh, no, it's an in-person. Great.
So, thanks for the opportunity to speak here. I'm Shayak, first year PhD student under Tony, and I am at Columbia, advised by Josh and Tony. Both of them are amazing students, amazing advisors. Sorry for that. So both of them are amazing advisors, but since it's Tony's birthday, I'm going to talk about how wonderful she is and how she has like taught me a lot about research in the last 2 semesters. So yeah, very happy birthday, Tony. And so working with her has always been really inspiring. She has been giving a lot of ideas, and it's like she has an amazing intuition about problems. And as Robert talked about, she has this her own way of thinking about problems and like providing directions, which like she has suggested us papers which she hadn't read, but she knew the idea and she knew how to use it, even though it was never obvious at the first look how to like have some applications in some other problems, which we later came up with. So she was always inspiring and supportive in that way. And she also like, she gave me the freedom to explore every other problem I wanted to. Like I was interested in computational algebra since my undergrad, and even though like she doesn't work too much on that, she gave us a lot of ideas and avenues to explore, which I'll come to again. And so moving on, I'll make it a bit more technical now. So one of the things I'm interested in is computational algebra. And one central problem in that is solving a system of polynomial equations. It's like you are given a set of polynomials, m polynomials in n variables of degree at most d, and it can be over any field or any ring, and you want to find a common root of that. And for the case of simplicity, we might assume that this field is just fp, where you have the polynomials mod p. And this is an NP complete problem because like it's an NP because if you have a root, you can verify if that is a solution or not. And you can arithmetize set to a system of polynomials. And there is different settings of this problem. So the input size is the number of monomials times the size of each monomial. And for p equal to constant and d being constant, free set reduces to an n-variate polynomial system. And there have been some works where there is this 1999 work where they can solve a system of polynomials over n variables having time complexity polynomial in d to the power cn and log p, where cn is a pretty large quantity. So Tony and I had some discussions on how to improve this. And well, as I said, she was always very insightful and gave motivations and great insights into other avenues. And she did like give an intuition for reducing this. The usual techniques of doing this is reducing all these polynomials to a single polynomial and then solving for roots. So she gave an idea, and that was a really nice one, but turns out that it was already present in this clean idea by Ryan Williams, who might be here, and others, where they solve it better than brute force, having a factor of p to the power epsilon n better than the brute force. And this also works in several settings, but I will not go into the details of that. Now, moving on from modulo primes to modulo composites, it's like this ring z by p to the power kz means you are working modulo p to the power k. And now this is a more difficult problem than working mod p, because this weird things happen in this case. So every element of mod p to the power k can be written as this sequence a0 plus a1p up to ak minus 1 p to the power k minus 1, where each of the ai's are from 0 to p minus 1. And why is this weird? Because if, for example, if we consider this polynomial x squared plus px mod phi square, there are p many roots of a polynomial of degree d for degree 2. For each of the I from 0 to p minus 1, it will give you a root, which is like kind of surprising that there are so many roots of one low degree polynomial. So an interesting question is how to find this modulo higher powers of p. And there's one term called unique factorization domain, which since it is not, I'll not go into the details, but this property not being satisfied makes these problems really difficult to entertain, difficult to solve. Now, we have, when we are solving some polynomials modulo composites, we will have roots of this form, where each of the AIs are mod phi from 0 to p minus 1. So a natural idea is to reduce this problem of solving mod p to the power k to solving several problems modulo p, which is like solving mod p is relatively more easy. So we reduce each of the AIs to over fp. And in order to find the first coordinate a0, it's easy to see that we can just consider f mod p and then find the root over modulo p to find a0. But now moving on to find a1, we can modify this polynomial f into a new polynomial, which is called f of a plus px, where a should be the first coordinate a0. And if you do that, you can intuitively see that if this has root a1, then the entire root would be a0 plus p a1. So if we reduce out the higher powers of p, this will exactly reduce the system to fp again. Now, this technique of finding a0 and then finding the next coordinate of a1 is also called lifting of roots, which is like not exactly same as the lifting of proof complexity. But so let's consider another example of mod p square. Notice that x cubed minus x squared plus p has two roots mod p, which are 0 and 1. So we first find the first coordinate, which can be either 0 or 1, and then we slowly move up to higher powers. Now, if we first consider the root 0, lifting would give us the polynomial 1 by p times f of 0 plus px, which is this polynomial, and you can see that mod p, this has no root, which means that the root 0 does not lift to mod p square. Whereas if you consider the other root 1, then you'll see that it gives another polynomial which does give a root mod p square. So the natural question arises that which root should we choose? So it's not just mod p square, but for higher mod p to the power k, we don't know which root we should select, which will lift all the way. It might so happen that you select some root which lifts to say k minus 2 and then stops lifting to k minus 1. So we want some technique to ensure that it lifts all the way. So there is this celebrated result by Hensel, which lifts roots and factors to any power of k, any value of k, but it only works in special cases. Building on this, there was this 2013 result which gives roots of univariates mod p to the power k, and they can find exactly the roots but cannot find the factors, which Hensel lifting can. So we noticed that how is univariate lifting difficult from multivariates? In order to do that, we kind of employ the same idea that we first consider the first coordinate a bar. A bar can now be seen as a vector in fp to the power n. It has n coordinates and it only consists of the roots modulo p, and then you will slowly move on to finding roots modulo p square. And in this way, you will reduce this problem again to finding solutions of a polynomial mod p, but and after that you will use the usual technique of solving over fp to find roots. But the problem in this case again is that the time complexity becomes very bad, that it becomes polynomial in d to the power cnk, where cnk is quite large. So it would be really nice to improve this exponent so that we can more efficiently find roots and factors of polynomials mod p to the power k, and so that we can generalize Hensel's lifting. That is, this only works when n times k is constant, but if we could do something better, then we could move up to higher k. And so this naturally gives rise to some open problems, which are like, when p is large, can we solve the system in d to the power n to the power c, where c does not depend on n? And we can assume that p is quite large. Or we could, Ryan Williams asked this question of whether we can improve the epsilon in p to the power 1 minus epsilon times n, where epsilon actually has some dependence on the degree and the prime. So if that could be improved, that would be really nice too. And also for solving mod p to the power k, can we do this better for some large p and large k? Because the previous technique was only restricted to very small constant k's. And factoring univariates and generalizing Hensel's lifting. So this is the kind of problems I am currently interested in. I'm also exploring a bit of more other problems with Tony on communication complexity, and she has been really helpful so far. And she has advised me in a wonderful way for the last 2 semesters. And I'm looking forward to several more. And thank you for everything, and happy birthday.
Thank you, Sai. Any questions? Online or in the audience? Thanks again.
Thanks.
I think we have one more speaker in the session. And that's going to be Noah Fleming. Just give him a minute to set up.
Yeah, so. Yes, I think I'm the last speaker for today. So my talk is going to be very relaxed and also pretty short. But I just kind of wanted to give like a fun little retrospective of my PhD. Now that it's done, and I can look back at this and laugh. And I guess the sort of takeaway from this is that it's good to work on hard problems. You may not always solve them, but you might solve something else that's also interesting. And you may cry a lot. Okay. Might not be connected to my computer. I can do it this way. Okay. So I'm going to start with my undergrad and kind of how I met Tony. So one day I went to Antonina's office and I'd heard about this thing called complexity theory, but I didn't really know much about it. I probably knew a lot less than she thought I knew because I basically just read the Wikipedia article and I thought like, sounds cool. Maybe I should do something with this. And so Antonina knew I had done a math undergrad, and she's like, you might like proof complexity. So I was like, guess I like proof complexity. And so the first paper I read was this paper by Tony and others. And turns out this is was a very influential paper to me. I didn't really realize that until like today. So here's two things that it mentions in it. Well, okay, I sort of knew it, but like, yeah, okay. The first thing is that it's not known, okay, it might be too small, but it's not known what the shortest proofs of the cutting plane, the shortest cutting planes proofs of the odd charge graph formulas are, or the Seiton formulas, or random formulas. Okay. So yeah, one open problem, Seiton lower bounds. The second one is that it talks about this. So in this paper, they prove lower bounds on cutting planes proofs with small coefficients, so these clique-color formulas and some other ones. But they also prove lower bounds on a sort of stronger proof system, which does this, they call it cutting planes with deduction. And Antonina and I looked at this for a little bit. But it is basically, you kind of augment cutting planes with a pre-processing step first. So you can take your unsatisfiable CNF formula and you're allowed to make this binary tree where you branch on threshold formulas. You branch on whether they're true or false. And then at each leaf of this balanced binary tree, it's important that it's balanced, you have little cutting planes refutations of the formulas together with everything along the path. So this is inspiration for something else. Yeah, okay, so first question that we decide to look at is like, yeah, is Seiton hard for cutting planes? And the second one is like, what can we say about like these cutting planes proofs with deduction when the case of the trees are unbalanced? Maybe what if we just restrict from threshold formulas to little integer linear inequalities? Okay, so I was already thinking about this in undergrad. Okay, so I should define what Seiton is. You probably all know, but you're given graph, maybe there's an odd number of vertices and variables for the edges, and it asserts that there's a way to like find edges, like say this edge is in the graph, such that every vertex has an odd number of adjacent edges. Of course, since the number of vertices is odd, this is unsatisfiable. Okay, and also I'll define cutting planes, but not so fun. Yeah, so in cutting planes, you prove that a polytope has no integer points. It's the same as refuting an unsatisfiable CNF formula just by encoding. You have this Vital-Gamori cut rule. You can take a linear inequality, which is valid for the polytopes. That means it lies outside the polytope. And let's say that the coefficients are integral, and you can round it up. And what this does is it shaves off some non-integer points of the polytope, but preserves integer points. So cutting planes proof is just a sequence of polytopes starting with your initial one and deriving the empty polytope. And because you preserved integer points, there's no, there could have been no integer points to make this. Okay. And then the other thing was, yeah, the other question was like, what about these cutting planes with deduction where you branch on linear inequalities and maybe have some unbalanced trees? My quickly drawn picture of what it looks like. Yeah, you branch on some integer linear inequalities and there's little cutting plane proofs as well. Okay, so I worked with Antonina for a while in Newfoundland, and then Tony came for a visit and we hung out for a bit and chatted about cutting planes. And I'm sure like half of it went over my head, but I enjoyed what I heard. And so I emailed her. And here is the first email I can find from Tony. I'm sure there were other ones, but they were sent to from an email address I don't have access to anymore anyway. So I got this like grant from the Canadian government to go down for a summer to Toronto. And this was one instance of the infamous Newfoundland to Toronto pipeline. I think there's been 3 people now that have come from Antonina to U of T. Robert is one of them. Yeah, okay. So then we worked for a summer on seems to be a rite of passage. at least I know Robert's gone through this. I think you went through this, Tony, which is reading a paper, which just takes months and months and months to understand. This was this lifting theorem for Shirley-Adams proofs to extended formulations. And I think I finally understand it now. So if you want to chat, I can explain it. Okay, we chatted a bit about Citon. Yeah, and we noticed that Tony do this, but you can efficiently prove Citon by branching on these inequalities. This will come up later. The high idea is you take the graph, you do like a balanced cut in the graph, and then you ask about the number of edges that are crossing the cut, and then you recurse on the side that has a violation. So easy upper bound. And sort of around this time also, I think we chatted with Russell a little bit about this cutting planes with deduction. He just suggested, okay, rather than doing these cutting planes proofs with leaves, well, let's throw that out and let's just do the branching. So we thought this was like probably a weak proof system. Okay, and so unfortunately, after working on this for quite a while, the best name we could come up with for it was stabbing planes. Okay, so stabbing planes, yeah, you've probably seen it. I should just define these things. It's, yeah, again, you start with a polytope or a system of integer linear inequalities, and it's a binary tree where each internal node is has two outgoing edges. They query whether an integer linear inequality is true or false. So you branch on whether ax is greater or equal to b or ax less than or equal to b minus b. And your goal is to derive the empty polytope at each of the leaves, because any integer point set is going to survive one of these two inequalities. You're not going to, if there were satisfying integer assignments to the polytope, then one of the leaves wouldn't have been empty. So here's a little picture. There's the little stabbing planes proof, and what happens at each step is you branch on branch on this inequality, and you rule out the fractional points in between. Okay, so at the end of my summer with Tony, she was really nice and sat down with me and like suggested all these places I should go, like apply for a PhD. And of course, a good student I ignored her and just applied to U of T. So glad I got in. But yeah, I don't know. It was a really lovely place to be. Everybody was really welcoming, really friendly. One thing that like really shocked me the first time I was there is that people were like treating me as an equal, which I don't know, was really weird because I was an undergrad. Like, why are you asking me what I think? I don't know anything. It's still true. Okay, so the PhD, I worked on many things, some related to complexity theory, some not.
You're about to cut that polytope with the...
The polytope is made of cheese, and also I'm about to cut it with some cheese. I found this while looking for another picture on my hard drive. Yeah, okay, so Citon and stabbing planes were still a main focus during this time with Robert and Dennis. And we made a little bit of progress. So we showed lower bounds on the following proof system, which I'm going to call cutting planes star proofs of Citon. And these proofs have coefficients of little o of n. I think I'm lying here, actually. I think there's a couple of caveats. First caveat that I remember is I think the coefficients have to all be positive or something like that, or maybe all oriented in the same way. And the second one is I think the proof may have a bug in it. Anyway, so this is going to be a theme. Okay, and then so some real progress. So this is when you know your PhD is going well. Your supervisor breaks her ankle. Sorry, Tony. So this meant that Tony was at home, like basically homebound, and really, really, really bored. So here's an example. Here's an email from 2 in the morning. This is just a segment of it. I looked at the email, it was like several pages. And at that time, we had been thinking about a lot of different things, kind of. We've been reading these old Krychek papers about these PLS games.
That she emailed herself.
Also, another funny thing is when I was going back through my emails, the number of emails that are called more of the same or same. Actually, if you go back here and if you zoom in on there, I have a printed out email from Tony that says same on it. Yeah.
Really impressive comment.
Yeah.
Josh, I got him to work on this problem. He was my first day. So many people, so-
Oh my God.
That's why it's more of the same.
Just forget which student it is. It's just, it'll eventually go through. Yeah, okay, so Tony broke her ankle, and we were, okay, weird. Yeah, so we were thinking about this paper by Krychek, talks about these PLS games, I think also this paper by Razgrov, and also reading some stuff by Mika, and I think Tony, that talk about this monotone sound. We kind of pieced it together is that this sort of more general interpolation thing where you can actually take any CNF formula and turn it into a like a cutting plane, take a cutting plane's proof of any CNF formula, turn it into a monotone circuit of containing some associated partial function. Okay, and we use this to show that random CNF formulas are hard for cutting planes. That's where this email from. And so then actual question, I think this is the first thing we tried was like, can we apply this to Cyton? Like, can we get this? So unfortunately, Cyton has small monotone circuits. This is why this problem, we thought, okay, this problem's really hard. This makes it a better problem to attack. Everybody thinks it's hard. So I should say caveat here, I don't think Tony really pushed me to work on this problem. I think she knew how hard it was and I just really wanted to work on it. Okay, so we had no idea how to approach it. And I think didn't work super hard on it, worked out on a bunch of other things at this point. And Tony and I worked on other things. So as a lot of you know, Tony has famously very broad research interests. But what some of you might not know is that Tony and I actually published an academic book on sword fighting. So if you, excuse me, I'm going to show you the book. Give me a second to make sure that it's pulled up. This might play music or it might not. I don't know if it's better that it does. Okay, I'll play the music very quietly. Anyway, so. So I didn't do this. I didn't make this. This arrived at my house. So, very proud owner of a book by myself and Tony on Legacies of the Sword. Also, this graph is a time versus skill graph, which is incredible. Yeah, so probably one of my favorite things that's ever happened to me. Okay, and then so we finally solved it. Sorry for everybody involved. I dredged this up from somewhere. This is the old attempt. Turns out that we had made an assumption, which I think was even in the old, even the result I mentioned before for the linear coefficients might have been in there as well. So it didn't work. Yes, there was a problem with this, which was that there are cutting planes proofs of Cyton. And so I'm going to redeem myself. I'm going to convince you that it's not my fault. It's the fault of these proofs in a minute. Okay, so what does this result do? What they do is they take actually these stabbing planes proofs that I mentioned at the start, where you do this like polytope. You pick the graph, you partition in half, and you query how many edges cross the cut, and you recurse. And then they translate it into cutting planes using this really weird way. And we kind of generalized this and showed that actually stabbing planes, if the coefficients are not too large, is equal to cutting planes. So you can translate it that way. Yeah, so but one thing about this is that it converts like these shallow stabbing planes proofs. Now the proofs of the Seitan formula, I think I say this actually. Okay, yeah. Converts shallow proofs into very, very deep proofs. So the proofs of the Seitan formulas that we gave in stabbing planes had quasi polynomial size and polylogarithmic depth. But the size and the depth of the resulting cutting planes proofs are both quasi polynomial. So what does this look like? Okay, so I didn't actually say how you can think of cutting planes depth, but like just like how in resolution you have a DAG and you derive things, you can think about cutting planes in the same way. And every proof has I think I say this probably, yeah. Every proof has a refutation sorry, every formula has a refutation of linear depth in cutting planes, but these proofs here have quasi polynomial depth, which is really strange. So they just look like one big long weird path. And the reason I say I'm going to redeem myself is this is a really weird thing to find. Like, how would you ever think of doing whatever is going on here? Okay. So a conjecture we made in sort of a newer paper is that any sub-exponential size cutting planes proof of the Seitan formulas actually has to have this polylogarithmic depth. Seitan has exponential size cutting planes proofs with linear depth. And so what we're asking is for a supercritical trade-off. If you restrict the size, then the depth goes like way beyond worst case. There's not many examples of these in the literature. Some examples are, there's a trade-off between resolution size and space. And most of these trade-offs are for resolution. There's a trade-off between tree-like resolution size and depth. And recently we proved a trade-off between cutting planes size and depth, but it really does not hold for Seitan. It needs a totally different technique. Okay, and so why is this conjecture interesting? It would mean that these cutting planes proofs are very difficult to find. They're very long and skinny. Okay. So I think that's everything I wanted to say. So this is the only picture I could find of me and Tony. I'm amazed we don't have any other pictures together, but it goes back to 2016 at Banff with Avi, baby me, and baby Robert. Yeah. Happy birthday, Tony.
Thank you. No, yeah, any questions?
Just to say that probably the most important for complexity theory thing that I learned from Tony is exactly the Newfoundland-Toronto pipeline. Biggest contribution to the field is connecting you and Robert to Tony. That's kind of obvious.
Couldn't go that far.
And Tony did it for me. Tony did it for me when I was an undergrad. She introduced me to Steve. So you see a trend? That's what I learned.
Any other questions?
Yep.
So their conjecture would imply superpolynomial lower bounds for given.
Well, we're just asking for anything super, like a supercritical trade-off. So really anything.
Right, but you can ask for something weaker, which is just a superpolynomial.
Yeah, that would also be great. Yeah.
So, but somehow it seems like since there's no exponential lower bound possible, you seems to not be interested in this.
No. Still interesting. Yeah, of course it would be interesting.
Yeah. I mean, it's a weird place to stop.
Any other questions? Does Legacies of the Sword mention stabbing planes?
I wish.
Yeah.
But the names are like uncannily similar
That must
in
be
a
why
way.
they made
There's
the
like a
mistake.
sword theme, you know.
So you've done a word search on those stabbing at all?
Oh, I should. I need to get a PDF of that thing. Sorry?
What's the book story?
Oh, the book story. It was. So I didn't fully tell it, but we like wrote this survey on Sum of Squares, turned into a book because it got really long. And then it was with these now publishers. We sent it there. They like sent us the first copies of the book, and it's like, oh, this is kind of fun. I got my own little book. I open it up and I like open the first page, and it just says Legacies of the Sword. And like very out of body, like surreal experience. So, but it's not even published by the same like company. Like it is not now publishers.
Did you ever get it fixed?
Yeah. They sent me some extras. Unfortunately, not extra copies of the same. But I wonder if they got a copy of our book. Oh no.
How's your sword fighting techniques now?
Very, very good. Let's go outside.
Okay, and let's thank Noah again. So before everybody leaves, Antonina just made a suggestion, which is